We all thought black holes were forever. These cosmic monsters swallow entire stars, trap light, and destroy everything in their path. But here's the shocking truth. Black holes can slowly disappear. They can evaporate. Not by exploding, not by fading away, but by leaking energy over trillions and trillions of years. This incredible discovery completely changed how we understand the very fabric of the universe. So, let's back up. What exactly is a black hole? Imagine a star, much more massive than our Sun, reaching the end of its life. It collapses under its own immense gravity, crushing itself down into an incredibly small space. The gravity becomes so powerful that nothing can escape its pull, not a spaceship, not a planet, and not even light itself. This is a black hole. At its very heart lies the singularity, a point of supposedly infinite density. Surrounding this is the event horizon, the famous point of no return. If anything crosses this invisible boundary, it's considered gone forever, or so we thought. This picture of a one-way cosmic trap seems simple enough. For decades, this was the accepted story. Scientists believed black holes only ever grow. They feed on gas, dust, and stars. They merge with other black holes to become even more massive. In this view, they were eternal fixtures of the cosmos, living forever. But there was a big problem with this idea. It seemed to clash with one of the most fundamental laws of physics, the laws of thermodynamics. These laws govern energy, heat, and disorder in the universe, and they suggest that information can't just be destroyed. But if a book, with all its information, falls into a black hole and disappears, where does that information go? Something just didn't add up. Physics was facing a major paradox. Then, in 1974, the brilliant physicist Stephen Hawking came along with a radical, mind-bending idea. He proposed that black holes aren't completely black after all. He combined the world of the very large gravity with the world of the very small quantum mechanics. Here's the core of his theory. Empty space isn't really empty. It's a fizzing, bubbling sea of virtual particles, pairs of particles and their opposites, antiparticles, constantly pop into existence and then immediately annihilate each other, disappearing in a flash. Usually, this happens so fast we can't notice it. But right at the edge of a black hole's event horizon, things get weird. Occasionally, one particle from a pair falls into the black hole, while its partner escapes into space. From an outsider's perspective, it looks like the black hole has just spat out a particle. This escaping energy is what we now call Hawking radiation. So, how does this make a black hole evaporate? It's all about Einstein's famous equation, E equals mc. Energy and mass are two sides of the same coin. When that lone particle escapes, it carries away a tiny amount of energy. To balance the cosmic books, the black hole has to pay for this energy by giving up a tiny bit of its own mass, and I mean tiny. For a black hole the size of a star, the amount of energy lost is so minuscule that it is completely unnoticeable against the radiation of the universe. But the process is constant. Over immense stretches of time, this tiny mass loss adds up. It's like an impossibly slow leak. This means black holes don't just consume. They also radiate. They slowly, painstakingly, shrink. Now, you might be wondering, how long does this cosmic disappearing act take? Don't worry, the black holes in our galaxy aren't going to vanish anytime soon. The timescale is almost beyond human comprehension. A black hole with the same mass as our Sun would take more than 10 to the power of 67 years to evaporate completely. That's a 1 followed by 67 zeros. To put that in perspective, the entire age of the universe so far is only about 13.8 billion years. Supermassive black holes, the giants at the centers of galaxies, could take even longer, perhaps 10 to the power of 100 years. So, while evaporation is incredibly slow, the theory says it is inevitable. What happens at the very end of a black hole's life? As it shrinks, its temperature actually increases. The smaller the black hole gets, the faster it radiates away its remaining mass. The process accelerates dramatically. In its final moments, a black hole would no longer be black at all, but a scorching hot, brilliant point of light. It would then likely release a final, tremendous burst of high-energy radiation, a flash of gamma rays, before disappearing from existence completely. No more singularity, no more event horizon. The matter and energy it once consumed are finally returned to the universe. So, why does all of this matter? The idea of black hole evaporation is more than just a cool sci-fi concept. It is one of the most profound ideas in modern physics because it connects our two best theories of the universe, Einstein's theory of gravity, which describes the large-scale cosmos, and quantum mechanics, which describes the bizarre world of subatomic particles. It also forces us to confront one of the biggest unanswered questions in science. What happens to the information that falls into a black hole? Does it truly get destroyed, violating the laws of physics, or is it somehow encoded in the outgoing Hawking radiation and preserved? Answering this information paradox could be the key to finding a single, unified theory of everything. In the end, black holes are not the eternal monsters we once imagined. They are dynamic, evolving objects, just like everything else in the cosmos. They are born from the death of stars, shaped by the relentless pull of gravity, and ultimately, erased by the slow march of time. This shows us that even the darkest, most powerful objects in the universe cannot escape the fundamental laws of physics. In the grand scheme of things, everything is temporary. Everything fades, even black holes. The universe is still full of mysteries, and we're just getting started. Thanks for watching.